The Earth intercepts only a minute fraction of the energy radiated by the Sun, less than 1/2 billionth. Even this seemingly insignificant amount, to our surprise, represents several 100,000 times the electric generating capacity of the United States. Solar radiation provides more than 99.9% of the energy that heats the Earth. Undoubtedly, the radiant energy from the Sun is the most important control of our weather and climate. According to Trevartha, the per minute energy flow from the Sun to the Earth is nearly equal to the total amount of energy consumed by man on Earth. Strikes the Earth's surface is that it is equal to about 23 billion horsepower. Actually, it is the amount of energy received from the Sun that acts as the driving force for all the atmospheric as well as biological processes on the Earth. Besides, all other sources of the energy found on the Earth such as coal, oil, wood, etc. are nothing but converted form of the solar energy. On completion of this module, you will be able to understand what is insolation, what are the factors affecting insolation, atmospheric depletion of the Earth's solar radiation. The word insolation is a contraction of incoming solar radiation. It consists of a bundle of rays of radiant energy of different wavelengths. The Sun emits radiant energy in the form of electromagnetic waves. The wavelength and the frequency of these waves, which travel with the speed of light, that is 3 × 10⁸ km/s, are nearly staggering. The longer waves, largely absorbed in the atmosphere, are called infrared rays. The shorter waves are called as the ultraviolet rays, representing the other end of the solar spectrum. It is a visible portion of the spectrum lying between the invisible ultraviolet and infrared rays that most effectively heats the Earth. In fact, the rays of the solar spectrum reaching the Earth's surface are converted after absorption by the surface from short wave to long wave radiant energy. This is what is known as heat. However, there are various factors which cause temporal and spatial variations in amounts of the heat. Various processes of the weather and climate are fueled by the energy gained by the Earth's surface and the atmosphere. Factors affecting the distribution of insolation. The actual amount of insolation received at a place on the Earth varies according to the conditions of the atmosphere as well as the seasons. The astronomical and geographical factors govern the amount of insolation received at any point on the Earth's surface. The first factor being angle of incidence, second being the duration of the sunshine, third the solar constant, fourth distance between the Earth and the Sun, and fifthly the transparency of the atmosphere. Angle of incidence. The altitude of the Sun, that is the angle between its rays and the tangent to the Earth's surface at the point of observation, controls the amount of insolation received at the Earth's surface. As the elevation angle decreases, the area over which the radiation is distributed increases. The vertical rays of the Sun heat the minimum possible area, but on the contrary, the oblique rays are spread over a relatively larger area, so that the amount of area over which the available solar energy has to be distributed is increased and the energy per unit area on the Earth's surface is decreased. In addition, the oblique rays have to traverse a larger distance through the atmosphere before they strike the surface of the Earth. The longer their path, the larger the amount of energy lost by various processes of reflection, absorption and scattering, etc. Thus, it is clear that the larger amount of radiant energy is destroyed in the case of slanting rays than in the vertical rays. Similar effect of varying angle of the Sun's rays can be seen in the daily march of the Sun across the sky. At midday, the intensity of the insolation is maximum, but in the morning and the evening hours it is reduced because of the slanting rays of the Sun. So is the case in winter and at the high latitudes when the amount of insolation received at the surface of the Earth is small. This is simply the effect of low angle of incidence. The major factors that determine the Sun's altitude or the angle of incidence are the latitude of the place, the time of the day and the season. The second factor, duration of the sunshine. The duration of the sunlight hours determines the length of the day, which also affects the amount of solar radiation received at the surface. Undoubtedly, the longer period of the sunshine ensures larger supply of the radiation which a particular area of the earth will receive. Obviously, the latitudes exercise the most dominant control over the duration of the sunshine and thereby the length of the day. The inclination of the earth's axis, its parallelism, the earth's rotation and the revolution, all these factors combine together to bring about seasonal changes. It is to be remembered that these astronomical factors not only cause differences in the altitude of the sun, but also differences in the length of the day from the equator poleward. At equator, the length of the day and night is 12 hours. On the autumnal and vernal equinoxes, they occur on September 21 and March 21 respectively. The midday sun is overhead at the equator. On these days, all over the earth, the days and nights are equal. On these 2 days, the maximum amount of insolation is received at the equator and the amount goes on decreasing towards the poles. But from the winter solstice, that is December 22 onward, the length of the day increases in the northern hemisphere till the summer solstice, which is June 21. On the contrary, during this period, the length of the day in the southern hemisphere decreases and the nights are longer. From June 21 to December 22, the length of the day in the northern hemisphere decreases and in the southern hemisphere it increases. In other words, at the summer solstice, the northern hemisphere has the longest day and the shortest night. The condition is reversed in the southern hemisphere. On the contrary, at the winter solstice, the southern hemisphere has the longest day and the northern hemisphere has the longest night. At the respective summer solstices, under cloudless skies, a polar area may receive more radiation per 24-hour day than other latitudes. It may be pointed out that because of the albedo of the ice and snow surfaces, the net radiation used for heating is largely reduced. Thus, the longer the period of the sunshine and shorter the night, the greater the amount of solar radiation received, all other conditions being equal. The third factor is the solar constant. As the energy emitted by the sun varies, the amount of insolation received at the surface also changes, but the percentage of change in the solar constant is rather negligible. The variation in the solar constant is caused by periodic disturbances and explosions in the solar surface. The sunspot studies that have been carried so far establish that when the sunspots appear in larger numbers, the intensity of the solar radiation received at the surface is increased. Naturally, therefore, as the number of sunspots decreases, the quantity of the radiation received at the Earth's surface declines. The scientists are of the opinion that the number of sunspots increases or decreases on a regular basis, creating a cycle of 11 years. However, there is little doubt that the magnitude of the effect of varying amount of solar constant on the amount of solar radiation received here on the Earth seems to be too small. The fourth factor being the distance between the Earth and the Sun. Since the Earth revolves around the Sun in an elliptical orbit, the distance varies during the course of a year. The mean distance between the Earth and the Sun is about 149 million kilometers. Each year, on about January 3rd, the Earth comes closer to the Sun, distance of 147 million kilometers. This position is known as the perihelion. On about July 4th, the Earth is a little farther from the Sun when the distance becomes about 152 million kilometers. This position is called as the aphelion. Although the amount of incoming solar radiation received at the outer boundary of the atmosphere is a little greater, 7% in the January than in July, there are other major factors such as the angle of incidence and the duration of the sunshine that more than offset its effect on the seasonal temperature variations. It may be interesting to note that the Earth is relatively closer to the Sun during the northern hemisphere winter. The fifth factor being the transparency of the atmosphere. Transparency of the atmosphere is an important control on the amount of insolation which reaches the Earth's surface. Reflection from the dust, salt, smoke particles in the air is an important mechanism for returning shortwave solar radiation to space. Similarly, reflection from cloud tops also depletes the amount of solar radiation that would otherwise be available to the Earth. The effect of certain gases, water vapor, and the dust particles on reflection, scattering, and absorption is well known. Obviously, areas with heavy cloudiness and turbid atmosphere will receive lesser amount of radiant energy at the surface, but the transparency of the atmosphere varies with time and place. Transparency of the atmosphere is closely related to the latitude. In the higher latitudes, the sun's rays are more oblique, so that they have to pass through relatively thicker layers of the atmosphere than at lower latitudes. In winter, when the altitude of the sun is relatively lower, there is greater loss of the incoming solar radiation than in the summer. Since atmospheric depletion plays a very significant role in the receipt of solar radiation at the Earth's surface, a more detailed discussion of this factor follows. Atmospheric depletion of the solar radiation. The loss of solar radiation in passing through the atmospheric layers is called as the atmospheric deflection. The figure depicts how solar radiation has to traverse thick and dense layers of the atmosphere in reaching the Earth's surface. The longer the path traversed, the greater the amount of radiant energy depleted. Various processes whereby heat energy is lost through the atmosphere are known as scattering, diffusion, absorption, and reflection. Scattering. The atmosphere is composed of molecules of air, water vapor, and dust particles. These molecules scatter the shorter ultraviolet waves in different directions. This process, in meteorological parlance, is known as the scattering. The solar rays consist of light and heat waves of different wavelengths. When the ultraviolet rays pass through such molecules as having diameters shorter than their wavelengths, manage to reach the surface of the Earth. Thus, when we look at the direct rays of the sun, we see more of the blue light, which was more readily scattered. At sunrise and the sunset, the oblique rays have to pass through the longest path of the atmosphere. Hence, all the color spectrums except red and orange are scattered. It is only the red and the orange colors that reach our eyes. This accounts for the reddish hue of the sky during the twilight hours. Diffusion. When the diameter of the particles is larger than the wavelength of the incident beam of light, true scattering does not occur, and the effect of the particles is of the nature of diffuse, reflection, or diffusion. It is effective for all wavelengths. Since the process of diffusion is non-selective, component colors of the incident light do not get separated. This is why the light reflected from a cloud when the sun is behind the observer is pure white. The sun, for the same reason, appears white when seen through a fog composed of water droplets. It is principally due to the diffusion of the light in all possible directions by the dust particles present in the air that we have sufficient working light before the sunrise and after the sunset. This diffused light is called as the twilight. The astronomical and the civil twilights last till the sun has sunk below the horizon 18 degrees and 6 degrees respectively. The twilights are of longer duration in the latitudes than in the low latitudes. It is of interest to note that it is mainly due to diffusion reflection that there is light in the rooms and under the trees. Thus, solar radiation suffers losses through diffusion reflection by larger particles such as cloud droplets, which occur in greater quantities at low latitudes in the atmosphere. There is difference in the effects of small particles and the cloud particles that are relatively larger. The molecules of small particles scatter a larger percentage of light of shorter wavelengths, causing the direct beam to reach in the red rays and the scattered light to be richer in the blue rays than the incident light. On the contrary, the larger particles in the cloud are incapable of producing any change in the relative intensities of the different wavelengths. When a cloud appears reddish in color, it should not be taken to be a result of selective scattering effect produced by the cloud particles themselves. It is on account of the loss of the blue light by scattering from the beam illuminating the cloud. Absorption has been defined as a process in which the incident radiation is retained by a substance and is irreversibly converted to some other form of energy. there is a certain amount of radiant energy loss by the process of absorption in the atmosphere. It may be pointed out that the gases do not play a very significant role since they are selective absorbers. The capacity to absorb solar radiation differs for different wavelengths. When a gas molecule absorbs light waves, this energy is transformed into internal molecular motion, which causes a rise in the temperature. Nitrogen is a very poor absorber of the incoming solar radiation. Oxygen and ozone are said to be the good absorbers of the solar radiation, shorter than 0.29 micrometers. At high altitudes, oxygen absorbs most of the ultraviolet rays. In the stratosphere, ozone removes ultraviolet radiation of relatively longer wavelengths. The most important and efficient absorber of the ultraviolet radiation is the water vapor, which along with oxygen and ozone absorbs roughly 15% of the total solar radiation within the atmosphere. In addition, carbon dioxide gas, which is present in the atmosphere in very small quantities up to the great heights, is an efficient absorber of incoming solar radiation that comes in the wavelengths of about 15 microns. In the direct absorption of the incoming solar radiation, the water vapor present in the lowermost layer of the atmosphere plays the most significant part. In the electromagnetic spectrums, a larger percentage is comprised of infrared waves. According to Ken Drew, about 43% of the incoming solar radiation is received through these longer infrared waves. A larger percentage of these longer waves is directly absorbed by water vapor. Thus, it is clear that the loss of the incoming solar radiation in the atmosphere is in direct proportion to the amount of water vapor present. Since water vapor is mostly transparent to the shorter ultraviolet rays and opaque to the longer infrared rays, acts as a screen to long wave radiation. The shorter ultraviolet rays pass through this gas clearly, but the longer waves of the incoming solar radiation are partly absorbed. Similarly, water vapor is an effective absorber of the long wave terrestrial radiation. In fact, water vapor is the most effective regulator of the surface temperature of the Earth. This effect of the atmosphere is known as the greenhouse gas effect. In a greenhouse, the glass walls or the glass roofs allow the shortwave solar radiation to pass through them, where it is absorbed by the ground and converted into heat. But the long wave terrestrial radiation is not allowed to escape the roof and the walls of the greenhouse. Thus, the heat inside the greenhouse is maintained. A part of the incident radiation falling on any surface is reflected back. It is called the reflection light. Thus, a certain amount of energy is lost and it does not play any role in heating the atmosphere. The reflectivity of a substance, usually expressed as a percentage of the incident radiation reflected, is known as its albedo or the reflection coefficient. It differs from place to place as well as from time to time in the same locality. It depends upon the amount of cloudiness and atmospheric impurities, the obliquity of the sun's rays, and the nature of the surface. The albedo for the Earth as a whole, also known as the planetary albedo, is 35%. It is to be noted that the clouds play the most important role in reflecting the incoming solar radiation back to the space. Another characteristic feature of the planetary albedo is the fact that Earth's land-sea surface accounts for only 4% of the total 35%. The albedo of water surface depends on the altitude of the sun. When the altitude of the sun is 47 degrees, the albedo varies from 3 to 5%. On the other hand, when the sun is near the horizon about 5 degrees, the albedo is found between 50 to 80%. So today in this lesson of insolation, we have read about the concept of perihelion, ephelion, understood what is scattering, reflection, deflection, and also the concept of twilight and the greenhouse gas.